All right, so today we're talking about 3.8, which is about Newton's method. So I don't totally remember Newton's method. I'm not even sure that I did Newton's method, but we're gonna remember it. And I'm not gonna try to sit and follow these steps. Just like normal, I'm gonna try to think about it, and we're gonna figure it out from there. So I do know that the gist of Newton's method is like, let's read the question. So we've got the function x squared minus 2, and we want to approximate the zeros. So we're going to think about that like the x-intercepts, right? We're trying to approximate the x-intercepts. So what we're going to do is we're going to do a linear approximation to this curve. So we're going to draw the tangent line. That's all that means, is draw the tangent line at a value, at really any value. They tell us to use x equals 1. So let's start by drawing that point at x equals 1. And we're going to draw the tangent line. So I can't perfectly draw the tangent line, but that's roughly what the tangent line would be. And what Newton's method is doing, it's trying to approximate this point right here, the 0, the x-intercept. So what we're going to do is we're going to do that approximation, and we're going to find that approximate x-intercept. So you see that's an approximate x-intercept. Basically, I'll say this was our first guess. So you see we went down there, we drew the tangent line, that was our approximation. Now we have a new guess, which is here. And now what we're going to do is the exact same thing. We're going to go to that point on the graph, and we're going to draw that tangent line. And dang, that's pretty darn close, ain't it? So that's Newton's method. And I would do it a third time. We're going to do it a third time in the math. It's hard to do drawing, but that's the gist of it. And so how do we do that? We'll think about how you just write the equation of a tangent line. We know how to write the equation of a tangent line because you just have the slope and you have the point. So to kind of bring it back to their notation and maybe develop the steps for ourselves, so let's write the equation of the line and use their notation. So we have our function, f of x. So we need the slope. So that means f prime. And we want the slope just at this point. So what do they call that? They call that x1. That's our first guess. That makes sense. So f prime of x1 is we want the slope at that point. And we're writing the equation of the line through that point. So point slope form, there's our 1 equals y minus the y value. Right, as we know, well, we're trying to do it just in general for now, right? That's why we're using x1 and x1. And then this is f of x1. So not f prime, just f of x1. And then what do we want to do? We want to find this x value. We want to find the x-intercept here. So how do you always find an x-intercept? When the y equals equal to 0. So we're going to make this y equal to 0 and then get the x by itself. Not the x1. x1 and x are totally different, but get the x by itself. So we're just going to divide and then add. So divide both sides by f prime of x1 and then add x1. So we get x equals x1 minus f of x1 divided by f prime of x1. And that's the process to get the new x value. Right? And that's just like from writing the equation of the line. That's not from trying to memorize Newton's method or anything like that. So let's use that to find our new point and see how good that approximation looks. And they want us to do it 3 times. So this will be our first iteration. So we'll just say, what is our x value? Well, I guess first we need f prime. So just take the derivative. F prime of x equals 2x. And now we want to run this equation. So we're going to say that x2 is 1 minus f of x1. So f of 1, so negative 1, over f prime of 1, which is 2. So that gives us that new point, 1 plus 1/2, so 1.5. So that tells us, wow, we did a pretty bad drawing then. That purple line should have been at 1.5. Looks like the parabola itself is at 1.5. But anyway, so that should be the new x value. So now that's one iteration. So now we want to do it again. So that's going to be 1.5 minus, let's see, f of 1.5. So 1.5 squared minus 2. Well, 3/2, so 9/4 minus 2 over 3 f prime of 1.5. Jeez. So what is that? Maybe I need to actually slow down here and make sure I don't make mistakes. So this is 1/8 up on the top. 1/8 divided by 3. That's 1/24. That's 3/2 minus 1/24. So that's 36/24 minus 1/24. 35/24. Jeez. Okay, that's 2 iterations. So we need one more. We should be pretty close at this point. So 35 over 24 minus 35 over 24 squared minus 2 over 2 times 35 over 24. And the whole point of this is not really to do it with a calculator, but to do it with like a 4-function calculator. So you can still use a calculator, but just a 4-function calculator that like doesn't involve square roots and stuff. Because they had access to that decently back in the day. But you could also just grind this out. That's also not that bad. So how are we going to grind this out? Should we just go to the 4-function calculator? Maybe we just go. But see, that's the problem, is I don't really have a 4-function calculator. But I don't need to sit here and like add and multiply fractions and stuff. So we need to double parenthesis that, because that's going to be 35 divided by 24. Close parentheses, square it, minus 2. Close parentheses, divide it. 2 times 35 divided by 24. So that's approximately, well, it's equal to, yeah, see why I didn't want to do that? 2,377 divided by 1,680. So approximately 1.415. And that is cool. I mean, what is the square root of 2? Pretty close. Pretty close. Could do one more and it'd be even closer, but we already got 3 decimals. So that's the idea. So it is nice to get it down to a step-by-step process. But all we're doing every time is writing the equation of the line and finding the x-intercept. And in fact, I would like to do that on Desmos. All right, let's try to make this on Desmos. I'm nervous that this isn't going to work out, but hopefully it will, and it should. Let me turn this off for a second so it doesn't block anything. My face won't block anything, unless we can at least do something like this. So let's see what we can do. So let's type in our function to get our base. Desmos is pretty good with using functions. So once we write it out like this, we'll be able to use it. So there's our function, f of x equals x squared minus 2. And now, what do we want to do? We want to have our x 1 as going to be our guess. So let's start it with 1. And I'd like to graph that point. So I'm not going to do 1. I'll use the variables. And in fact, I'll even use f. So I'll say, let's do a point where the x-coordinate is x1 and the y-coordinate is f of x1. So there's our point there on the graph. And now I want to write the equation. Well, I want to display the equation of the line, at least. So I want to write the equation of the line through that point. I guess I could call that a point. That's our point. So then I can actually use p.x and p.y, the x-coordinate and the y-coordinate of p, which is pretty good. Well, what do I need to actually write the equation of the line? So I need to take the derivative. I don't actually need to separately define that. Desmos can very nicely understand what f prime means. So I can say f prime of x1 times x minus x1. Oh, right. No, that's the whole reason I did p dot x plus y p dot y. So there we go. And now actually, yeah, I can drag this point around, and that'll allow me to drag our tangent line around. Beautiful. But that's not what I want right now. What I want right now is to graph this point. Which, what is that point? That's where the y value equals 0. So how is that going to go? The x value where the y value equals 0. So I guess that's actually what I'm doing down here. So that's going to be should I do it as a function? Let me not do it as a function first. It'll just be like x equals negative p dot y. Right, and this was the formula we were just using when we were on paper, of course. Divided by f prime of x1. And then plus p dot x. Right, and so see how that's finding that y-intercept there. And I actually want to make this an action is basically what I want to do, right? But I want to do one more thing. I want to do a line going straight down from here. So for that, I just want to do a parametric where the x value is x1 and the y value is t, where t goes from 0 to x1 to f of x1. But yeah, that doesn't work out then because of that. That's kind of a problem. Oh, no. That's not what I need to do. I need to do a set of points, which is x1 comma 0. And x1 comma f of x1. And then you can do 2 points, and then you can connect them with a line. There we go. I don't know what the best color is to make things. And then really what I want is I want this to be an action. I want F1 to go to that. And then look what happens when you do that. This should just run the method. It should take this point that you just saw was 1.5. It's going to take this x-intercept. It's going to draw the vertical line to get to that point. And then it's going to make a tangent line at that point and then find the x-intercept. Boom. Yep. It never did graph the x-intercept. You know what, though? I need to do that. I need to graph, what is that? The x value? That, comma, 0. So see, that's your approximation. You run it again, it's going to do the exact same thing. Yeah, look how close that gets after 4. My goodness. Oh, that's beautiful. That's beautiful. And that'll work for any equation. You know what? I should put this separate even so you can actually see what it's supposed to be. And of course, it is intended to be the square root of 2. And if we do that long enough, yeah, you see it right now. It's right on, according to Desmos. That's beautiful. That's beautiful. And what's really beautiful is like we started at 1, so we started pretty close already. But if we started really far away, it should still go there. And I think it'll go there decently quickly. So it goes to 5, and then to there, and then to there, and then it goes right in. So no matter where you start, it'll always go there. Now, if we start, what if we started right at 0, actually? If we start right at 0, it breaks. Wow, it actually says it equals infinity. Very interesting. So if we start right at 0, it breaks because it doesn't know which way to go. But if we start on either side of 0, it'll work just fine. It'll just go really far away first. Very interesting. Very interesting. But this is great. So we can use this to check our answers for all the other problems that we do. So let's go back to it. So the same thing. Use Newton's method to approximate the zeros of this equation. So how are we going to make sure we get all of the zeros? That's an interesting idea because we're going to have a few of them. We might have 3 of them, right? So we're going to have to do a few different starting values. Because I don't want to just look at it and say we know the answer from there. So let's remember, I guess it is worth remembering. That's the general formula. Do these steps tell us about starting values? Oh, I guess the whole thing is these don't have real zeros. So I feel like we should just do it without graphing it. So we can start at 1 again. Unless it breaks. So let's see. F prime of x is 6x squared plus 2x minus 1. So if I start off with x1 equals 1, then x2 equals 1 minus f of 1. And should I just run synthetic here and say the remainder is the answer? That is how that works, right? I always forget how that works. Although here it's easy enough to just plug in 1. So I'll just plug in 1 and say that it's 2, 3, 2, 4. So if I run this, do I get 4? I get 3. What? So did I just screw it up? 1. So 2, 3, 2, 3. Okay, yeah. So that is how it works. If you plug it in, the remainder is that. So 1. What was that all to say? F of 1 is 3. F of 1 is 3. F prime of 1 is 7. So that's 4 over 7. X3 is 4 over 7 minus... Oh my gosh. I mean, how hard do they want us to approximate these zeros? Should we be looking at a graph? I just feel like that's a lazy way to do it. Let's do 1. Well, I feel like we also need to figure out how many zeros this has. And that's why you should look at the graph. Here's the problem. I didn't write the textbook. I don't know exactly what they're going for here. Let's see how easy it is to run 4/7 in synthetic. 2, 8/7, 15/7. Not that easy. 60/49. Well, that makes it better. 11/49. Yeah, but you're rocking a 7 cubed. 44 over 7 cubed. And then adding them. That's kind of ridiculous. And then dividing it by another ridiculous thing. So, I feel like we get the gist of that. Maybe we can just look at our nice thing we made and use it. Because it does ask us to use the graph, if we're being honest. So, if we look at this graph, are we going to find that there's multiple zeros? No, there's just one. And we did an awful job of approximating it so far. So, but that's just our problems? They do just want us to look at the graph? So if I look at the graph, I would know that I should be using -1, I suppose. But that would be the only difference, is we just use -1. Why did I write -1 there? I didn't use -1. I should be using -1 though. So then -2, -1, 1, 0, 0, 1. So you just get 1 when you use -1. So you're going to have -1 minus 1 over, when you plug in -1 to here, it's a +6 minus 2 minus 3. So 3. -1 minus 4/3. So -4/3. And I suppose that would be a bit easier, although that's already pretty far on. And you see that is what we get when we do this right here. Can I even get what the answer would be? I guess that'd be pretty difficult. But here, let's see. So if I started at -1, and then we go, there's our -4/3 we just got. If we did it again, -1.233. And then, I mean, that's pretty much right on. Yeah, you see, you click it more, it doesn't even change. That's as right on as it gets. Oh, yeah, you can just drag it too. Yeah. So that's pretty good. Doing these by hand, see, I don't really get the purpose. It's nice to know the idea. It's nice to be able to code it up in Desmos. Speaking of which, let's go to the next problem while we're here. So the next problem says that the function x to the 1/3 is not differentiable at x equals 0. And then they want us to show that the Newton method fails to converge when you start at point 1, which I was a little surprised by, because I thought that it would end up going, oh, well, that's kind of the problem, is that it's straight up and down. So let's see what this does. It'll still work and do stuff. Oh, but it goes farther and farther away. Oh, no. Oh, no. Because it likes to go towards, like, flat slopes. Well, actually, no. It's supposed to go towards 0. Oh, no. Yeah, it goes further and further away. So if your 0 is at a not differentiable place, it won't get it. If it's got x cubed, that's not a problem, though, right? And you should just be able to start at that and get it still. Yeah, this is working just fine. Oh, that's beautiful. That's really nice. That's really nice. I wonder if you can do it without actions. Probably. Oh, and that was the last one. No, I almost just want to play around with this more. Wait. Oh, shoot. Did it not converge all the way to 0? Or did I just not click it enough? I just didn't click it enough. There we go. Wow, they give me a lot of decimal places. Yeah, it makes sense. It shouldn't ever go to 0. It only goes to 0 as you do it infinity times. So that makes sense that it's not actually 0. I'm just surprised it's not rounding it to 0. Very nice. Very, very nice.